Okay, so today we're looking at binary and linear searches. We'll talk through how they work, the algorithms for them. We'll look at some code as well. Just to start, you've got three flowchart symbols and three sort of names for them. A quick sort of pairing exercise. I'll pause and give you a chance to have a look at them. So the top one's a process, the middle one is a decision, and the bottom one is a terminal or terminator, which is your start and stop point for your flowcharts. So specification content within this sort of section we're looking at is just to basically learn about linear and binary searches. I'm going to spend just a quick touch on the requirements. I don't normally, but for this lesson I will. So understanding the main steps of each algorithm. So we're going to understand how it is that a linear search and a binary search actually run, any prerequisites of the algorithm, and this is important, and it will become apparent why when we look at this later on this lesson. Applying the algorithm to a data set, it's actually just running through this practically, and identifying an algorithm if a given code or pseudocode is presented to us. So we'll look at what this looks like if we were given the pseudocode or the exam reference language version of it, as well as the actual Python code for both of these searches. So first of all, it's worth kind of identifying what we mean by the term searching. Now, it may seem really obvious and apparent, but it's that idea of looking for something. So computers search for things in a similar way we do. So if you're thinking about the fact that if you were looking up a word in the dictionary, you might find a reference point, use that reference point to kind of navigate your way through the alphabet until we get to the word that we're looking for. If we're looking, for example, through a stack of papers for a particular test, for example, we'll just start maybe from top to bottom and flick our way through until we get to there. But there are some certain things that will change the way in which we search, and we'll talk and explore about those in a bit more detail. So first of all, let's look at a linear search. Now, linear search is probably the most straightforward of the two. And essentially, a linear search is where we start from the start of our list or from our whatever it is that we're looking for at, and we just go through from a top to bottom. So in the example that I've got on screen, I've got on there at the bottom apple, orange, banana, pear, lemon, and grape. And if I was looking for the word pear, I would just start at the start of the list and I would say, okay, is pear in the first item? No. Is it the second item? Nope. Is it the third? Nope. Is it the fourth? Yes. And I just keep going through the list one item at a time until I find the value that I'm looking for. And this could be done in any number of ways. And it's worth noting as well at this point that whilst I've used words in this example, it could be numbers, decimals, or any sort of data type. So just bear that in mind as well. So a linear search, ultimately just starting from one end of the list, working our way through the list until we find the item that we're looking for. And we can write this as an algorithm. And here's an example. So we might check the first item. If it is what you're looking for, then stop searching. Else, move to the next item and repeat until you've checked all elements. And it's worthwhile noting that obviously you might end up being in a situation where what you're searching for doesn't actually exist in the list. And if it isn't found in the list, the idea is that you would have gone through all the items and found no match. Now, binary search works in a slightly different way. It's more efficient, but it is also more complex. So binary search, firstly, works only with ordered lists. So what I mean by that is your data has to be in some form of order, be it alphabetical or numerical order, for a binary search to be able to function. A linear search doesn't need to be in order, but a binary search does. And that's because we need to find the midpoint in our list. And it's important that if things aren't in order, so if we were to say the numbers 1 through to 10, and we were looking for a number and they weren't in order, this method isn't going to work. And hopefully that will become apparent as to why. So in this example, you can see I've got a list 1, 2, 3, 4, 5, 6, and 7 across the bottom. Now, if I was looking for the number 6, what I would do is first find the midpoint in this list. And in this scenario, 4 is our middle value. What I would then do is establish whether or not the value I'm searching for, so in this case 6, is greater than or less than my midpoint. Now, 6 being greater than 4, I immediately know that I don't need the number 4, and I also don't need anything less than 4. So I can completely disregard everything to the left of the number 4, including the number 4, which then just leaves me with 5, 6, and 7. And I repeat the process again, where I find the midpoint of my list, in this case 6, at which point I've found my value. And I would keep repeating that for whatever size the list is. And I'll show you some examples of these in practice as well. The algorithm then for a binary search. So we would take the middle value. We'd compare the middle value with your search item. And if it is the value you're looking for, then you stop searching. Else, if it's larger than the search item, you disregard the right-hand side of the list. If it's smaller than the search item, you disregard the left-hand side of the list. And you repeat that until the item is found. So each time you go through, you'll effectively be getting rid of half of the list of data. You can see hopefully how this is a much quicker process. This animation demonstrates this quite nicely. And you can see that the binary search has finished much quicker and taken only 3 steps, whereas whilst the second search at the bottom is labeled as sequential search, this is in fact a linear search as well. And you can see that in the linear search, we're just going through the list one after the other till we find the value 37, and it takes a significant number of steps more than what the binary search does. Now, obviously, this is on a reasonably small list. If this list was much, much greater, much bigger, you can start to consider the fact that it's going to take a significant amount of time. If you're talking about something like the NHS records, where there may be 70 million records, it can't really be a case that you can spend the time looking through all of those records to find a patient's details if there is time pressures in terms of getting them the required treatment. Whereas a binary search, being a quicker method of searching, may well obviously speed up that process. So hopefully we have a kind of an understanding as to how these two work. It is going to step up in its sort of technical element of things now. So when we look at the comparisons of the two, so the first thing to note is that, as I mentioned, a linear search works on both an unordered and an ordered list. Whilst it doesn't have to be ordered, you can still perform a linear search on an ordered list. So basically the data can be in any organization at all, and a linear search going through one by one works. Whereas in a binary search, it would need to be in order first. If we look at the complexity of the algorithms, so if we had to write an algorithm for a linear search, it would be relatively simple. Whereas a binary search, if you flick back a few slides, you'll see that it's a sort of more moderate, it's a slightly more challenging algorithm. The length of time to complete. Now, in the case of a linear search, the worst case scenario will be that you'll end up having to search every single item, and it will be the final item in the list that you're looking for. Even if it's a value that's not in the list, you'll still have to go through every single item in that list. And as I mentioned, if we're talking about medical records, 70 million records as a kind of random sort of figure, it can take a long time. With a binary search, the worst case scenario, if the values aren't there, is that you'll have to search through half of that list because you'll be cutting it through half at a time. When it comes to coding these, a linear search is sort of moderately difficult to code. It's not impossible, but you may find it a challenge. Whereas a binary search can be quite tricky and quite challenging to consider in how you calculate the midpoints of the list. But I'll show you some examples of the code as well. Now, this is how your exam may be presented to you. So if you were asked to sort of identify which search method this is, the exam could present it to you in this way. Now, this looks like Python, but again, this is that exam reference language where there are some differences. There's some annotations in red to kind of say what the code is doing. And if this is your first time looking at this, this may be a little bit challenging at the moment, but it may be a case, obviously, in future, revisiting this, you'll have a firmer sort of understanding. So I'll pause, or we can pause the video, have a chance to read through this and follow what the algorithm is doing. And then I've taken this and I've converted it into Python code. So this is the same exam sort of presentation, but converted into Python code. So you can see how you might actually program a linear search. And this is a simple search where I've got a list of fruits, and then I'm getting the user to input a name for the fruit, which then runs a function which searches through that list to see if what the user has entered is actually found within there. So it doesn't say where it's found or anything. It's just a simple, does it exist in that list? And you can enhance this code to actually tell you where in the list it is, amongst other things as well. But this is just simply saying, does it exist within the list? And the same again for binary. So this is the exam reference language version of the binary search. And again, there's comments there for you, and I'll pause to give you a chance to have a read through this. And then again, I'll show you a Python representation of this algorithm. So this is the Python code again for a binary search. It may not look massively more complex at first appearance in terms of the complexity, but when you start to consider that there's more maths within it and there's sort of different features that are being used within this program, it is a higher level of complexity than that of the linear search. But this works on a basis of a series of numbers 1, 2, 3, 4, and 5. The user inputs a number, and then it will just again tell you whether or not it's found within that list. Again, you can enhance this to tell you whereabouts it's found and so forth. But for this simply is just to say whether or not it's found. There is a point and a question that quite often gets raised as well, is with a binary search, what happens if we haven't got an apparent or obvious middle value? So where a lister has an odd number of elements, it's quite clear where the middle value is. So if we were just looking at a list of the numbers 1, 2, and 3, it's evident that the number 2 is the midpoint. Whereas if you've got an even number of elements, so 1, 2, 3, 4, 5, 6 in this scenario, the midpoint falls between two numbers. In which case, how do we decide where it is that our midpoint goes? Now, if you use the computer to calculate the midpoint, it will come out at and round it up to the value just to the right of the midpoint. So in this case, 4. Now, the thing that I would say is that fundamentally, it makes very, very little difference in the efficiency of the algorithm. So I wouldn't panic too much whether you chose the left or the right-hand point of it. If you're using the computer to code it, that will automatically take care of it for you. But again, as I say, has very little impact on the efficiency of your algorithm.